which one is more positive. So for example, if BN1 had a +1 volt and BN2 was at 0 volts, BN1 is going to be more positive, and that's going to bring our op amp into saturation and send it into 90% of our voltage source coming out of D out. If BN2 was more positive, then it's on the inverting signal, and then it's going to go to our negative saturation. And so we kind of covered that one. And so we do have a lab on that just so that we can prove that out and take a look at that, just so we know how to hook them up. Now op amp as a comparator, because that's a lot of times what we do. All right, so let's go to our first one here that I want to. So basically what we have here is we have the same thing. This is, the only difference is that we're just tying our inverting pin to ground. So basically it's an open loop comparator. The only difference is that pin 2 is always going to be at our plus and minus 0 volts. And then depending on whatever Vn is going to determine what our output is. So for example, if we had plus 2 volts on our Vn, and I have a voltage source of 12 volts. What's going to be my saturation? What's my maximum voltage I'm going to get out on V out?
90% of whatever.
Yeah, 90% of whatever our voltage source is. So some of you guys that were working on the labs ahead of time there forgot about that. That it's going to be, you don't take whatever you measure. It's actually, you know, for our approximation, it's just 90% of our voltage source. So our V saturation is going to equal to what? How many volts?
10.8.
Yeah, 10.8 volts. That's going to be either plus or minus 10.8 volts. So my pin 2 is always at tied to ground and gives me my plus or minus 0 volts. If I put in a positive 2 volts, what's my VL going to be? So it's just an open loop comparator. It's going to be our positive 10.8 volts. Then if I put V in as a negative 2 volts, what's my VL going to be? Negative 10.8 volts. So remember when you're analyzing these, if you just take a look to see which one's more positive, when we're looking at an open loop comparator, we're just looking at which one's more positive. So is my negative 2 volts more positive than my 0 volts, or is my 0 volts more positive than my negative 2 volts? By 0 volts. So you just kind of draw your arrow down and just say, this is more positive, look to see what sign it is. So if this one's more positive, then it gets inverted and it becomes negative output. So the same thing here. So if I end up with a plus 5 volts, what's my VL going to be? Positive 10.8. Okay, so it's just gonna kind of flip flop back and forth. So these are our 0, and it's all going to be relative to our reference point on our pin 2. So if I have plus or minus 0 volts on there, what's my VL going to do?
Probably more positive.
You don't know for sure. Yep. So a lot of times they go positive, but I think Tyler, you had one that kept on going negative.
It just did once.
Or just once. Yeah. So we really don't know which way it's going to do. if they're both equal going on to our input. But we know that it's going to go into some type of saturation because of our input biasing currents area and our op-amp, the characteristic. It really wants to bring it down to 0 volts, but it can't because of the gain. There's going to be that offset biasing inside the op-amp. So to make this thing definitely predictable, what's our difference between our input pins that we have to have? How many volts do we have to have that voltage in between the two input pins to make it predictable?
Difference of 1.
2 millivolts. Okay, so always remember that it always has to be greater than 2 millivolts before it's determined. So if I had this one at plus 2 millivolts, then my op-amp is going to be predictable and it's going to go what? Positive 10.8 volts. So we always have to have at least 2 millivolts difference in between there to make sure that we actually end up switching our op-amp into the right direction. Alright, so let's take a look at that. So a lot of times what we're doing, we're using these things as triggers. You know, we're looking at some type of a signal and we want to trigger. It could be this op-amp might be triggering another relay to turn on a heat controller or a motor controller or something. And so they're really basically what they are, they're just triggers. And we're just telling you what we want to trigger at. And that's our reference location. It's just telling us, okay, I want to trigger anything that when it becomes at 0 volts. So let's take a look at the most easy signal on when we're looking into an op-amp. Is that we're going to send in a triangle wave into our VN. We know that this is going to be, my reference voltage is going to be plus or minus 0 volts. We have a triangle wave, so we're going to put in our triangle wave. Here's my 0 volts DC reference. And we'll send it up to 3 volts V max. And we'll send it down to 3 volts, negative 3 volts V max. And then we want to take a look and see what our output is going to do as we're sending it in there. So as I start putting this triangle wave in there, we want to see what happens to our output. So when we're looking at these waveforms, we know that this triangle wave, it's starting out at 0 volts. So at 0 volts, we're going to look and see what the output is. So at 0 volts, what's my output going to do? It's going to be positive or negative?
Don't know.
Don't know. We don't quite know yet. So we really can't determine what our output's going to do at 0 volts. We really don't know what it's going to do. So what we're going to do is we've got to know that at our 2 millivolts, so as it starts going up to our 2 millivolts, at that point when it goes up to at positive 2 millivolts on our triangle wave, what's my output going to do?
Go positive.
It's going to go positive. And it's going to go up to our saturation, it's going to go up to our plus 10.8 volts. So right there at our 2 millivolts, this is really where right at this point, I need to get one more marker here. Grab my green marker. I think I bring them into the other room.
That's Tom's way of getting back at you with all the paper.
So right at this point here, and right at our 2 millivolts, this is what we're going to call our upper toggle point. So this spot right here, this is our UTP, our upper toggle point. That's where it's taking that output, and it's going to go from a low up to a high. Then as long as this thing is always staying more positive, my output is always going to stay high until it gets down to that approximately 0 volts again. And that output is going to go, and then it's going to switch, and it's going to go negative. Now, at this lower toggle point, though, again, we have to have that toggle point so that it's predictable. If my reference voltage is at 0 volts, my actual lower toggle point is going to actually happen at what voltage?
Negative 2 millivolts.
Negative 2 millivolts. It's going to have to go down to that negative 2 millivolts before it becomes predictable. And so, at this point here, this is our lower toggle point, and that's going to happen at approximately 2 millivolts, depending on how your op-amp characteristics works. And then that's just going to go ahead and it's just going to kind of repeat itself and keep on going. So we have upper and lower toggle points. That's what we're always looking at. We're looking at, okay, where are my toggle points at? So mine are going to toggle at, every time that this thing, ideally we would say it's going to toggle every time it goes at 0 volts, but it's really going to, what you're going to find out, it doesn't. And so the people that already did the lab, and when we superimposed on that, we brought these two signals, we brought our signal down on top of our output, and we superimposed them, and let's see if I can draw this here. Here's our 0 volt. What we found out that if we zoomed in on this little area here, because that's what we like to do, we take our oscilloscope and we really find out what's going on. When we zoomed in on that area, we found out that, first of all, this thing's going to have our op-amp is going to have a slew rate. But when we zoomed in on that triangle wave, we could really kind of spread out our time, get that line flat, and then our square wave, that one had a kind of a slew rate, but not as much. And that kind of went up as more of an angle like this. So here's our blue line is our triangle wave, and then our purple line is our square wave that's zoomed in, both on time and amplitude. So we really zoomed in on that area. And what we found out that if we could actually physically see where that was really actually toggling. So here's my 0 volts right here. And we found out that it was really actually happening above 0. We could actually really physically see what the true toggle point was on that op-amp. And some of them were up around 100 millivolts to 200 millivolts. But that's your true toggle point, is where it is. Ideally, you want to say that it's at 0 volts, but in practical purposes, it's not. It's going to happen above it. And then if I went and did my other triangle wave, went down below, and then my other slew rate coming off my output, so this is the falling edge of my thing, and 0 volts was here again. We knew that it didn't toggle until it got down below that 0 volts. So zoom in on that when you're doing your lab, zoom in on that area and see what your actual toggle point was. Just superimpose them, make sure that your reference voltage of your, remember when you're looking at your oscilloscopes, you have a little arrow on the left-hand side, that's your 0 volts. That's what's identifying as your 0 volts. So bring your channel 1 and your channel 2 right on top of one another. Superimpose them and then put your signals on top of one another, and then zoom in on that area and find out exactly where your toggle points are. Okay? So we can go ahead and we can, so if we're always trying to turn something on, a relay or whatever it is, so, if it's, if it was, if we're looking at, let's say this is like because we're looking at that first waveform here, at 0 crossing with it being a positive, and it's going high, this might be like a cooler or something like that, or an air conditioning unit. And it's just saying that once you get above 0 volts, and that 0 volts could be relative to temperature. You know, at 0 volts it might be, 70 degrees or whatever our process signal is. So we're just saying that anytime you're above 70 degrees, turn on the output, and that turns on our air conditioner. Then when you get to 0 volts again, back down to 70 degrees, turn off that air conditioning unit because I'm back at 70 degrees, and then it shuts off. And once it gets above that 70 degrees, it turns back on, and then back off. So it's just kind of a, we use a triangle wave to simulate another type of a signal, and it could be, it could be a temperature curve. We might, when you go into some type of a room or something, you go and turn on your heat and air conditioning unit on there. And what's going to happen? Let's say we're starting out at maybe 60 degrees, but you want to get up to 70 degrees. What's going to actually happen is that you're going to start heating up, and it's going to overshoot, and it's going to undershoot, and it's going to overshoot, and then eventually it's going to kind of stabilize itself out until it gets to 70 degrees. Okay? At 70 degrees, depending on how our process control is, we might say that at 70 degrees, this signal going into my op amp might be equal to 0 volts. We just say at 0 volts, that's my ambient temperature. So anytime the signal starts to go above or below my 0 volts, so we'll say here's my 0 volts. Anytime this thing goes above my 0 volts, it's going to turn on the air conditioning unit. Then once it goes below the 0 volts or my 70 degrees, then it might go ahead and turn my heaters back on. Then it's going to turn my cooling back on, and it's just going to keep on doing that. It's going to keep on turning on my heat and coolers until it stabilizes out, and then hopefully once you get it stabilized out, then it's going to kind of, that signal's going to sit there, and these things are going to, the output's just going to keep on toggling back and forth to try maintaining that 70 degrees. And eventually it'll stabilize out. Now that's in its basic form, but we actually really have what we call PID controllers that actually have a sophisticated, more circuit into it. This is a very simple one, a very basic one. But we actually do have PID controllers that are, can't remember, proportional, can't remember what the ID stands for. I'll think of it, I'll look it up here. But what a PID controller does is that it can be predictive. So once that heat starts to, or once it, say if right here we're too hot, we're above 70 degrees, it's going to turn on our air conditioning unit. What actually happens is that by the time it gets to this point, it knows that it's going to start cooling. So what it does is it starts cycling the output so that the cooling isn't constantly on, so that we keep on getting the overshooting. What happens is it starts doing another oscillation inside here and turning on and off that air conditioning unit, so that by the time it gets down to 70 degrees, it doesn't overshoot it. It's already starting to back away of how much, how long it's on for. It just kind of changes the duty cycle. And it gets to be very predictive. It starts turning on and off at a faster rate and longer times in between there, so that by the time it gets to 70, it's not going to go and overshoot it. So they're kind of like the basics of a PID controller. So we can kind of predict and get stuff leveled out and stuff. And that's how we're using it. We're just using it, we're comparing it, comparing this, our signal in, to a reference voltage. And we can set that ratio for whatever we want, to whatever we design our circuit for. We can set that 70 degrees, or we can make this 80 degrees at 0 volts, or whatever we want. It all depends on how we design our circuit. So a lot of times we'll just use a triangle wave to simulate our signal. And that way we can see what does it look like. So we'll put a function generator in there and see that if our design is what we wanted. because this might have been critical. Maybe this 2 millivolts difference here might have been critical to us. Maybe we can't make sure that we can't have that. So maybe we need to put in a voltage divider in a reference voltage and set it for a negative 2 millivolts or a positive 2 millivolts. And we can make an adjustment on our pins too. And that would be our new reference voltage, and that would be our mix selector here. Threshold one. Okay? Any questions on that? Does that all kind of make sense? All that?
That's pretty cool, Kurt. So this is kind of like the thermostat in your house?
It's just like a thermostat in your house. Yep.
Cool.
And so you can make yourself a thermostat.
Yeah.
Yep. In a very basic form.
Right.
Like I said, we have what we actually have is PID controllers, because it will, if I don't have a PID controller, if I turn on my heat, it's going to get up to so if I say, let's say I'm below my 70 degrees, let's say I'm at 60 degrees, what's going to happen is it's going to keep that heater on until 70 degrees, and then it's going to shut that heater off. Well, we have that residual heat that's in our heat exchanger. So that heat is still going to, that heat coming out of there is still going to heat up our room. So then it overshoots. So that's what that PID controller does. It gets to be predictive. It says, by the time I get to here, start turning off that heat exchanger so that it starts cooling down and doesn't keep on heating up the room after I shut it off. And by the time it gets to here, then hopefully it stabilizes out. You're always going to get a little bit of ripple, but it's going to start out really big. It's going to undershoot and overshoot until it learns your heat exchanger. And what we call that is auto tuning. We can actually do an auto tuning, and it'll learn the characteristics of your heating elements or your cooling elements. It knows after it runs for a half hour to an hour, and it does an overshoot several times and stuff, it understands how the characteristics of your furnace is or your heating element. It'll be predictive. It knows that depending on the wattage of your heater, if I turn, like, let's just say I like a hot plate or your oven or your stove top or something like that. Let's say I had a 1500 watt heating element, and I plug it into my 120 volt AC. I plug that in, and it's not gonna heat up right up to 1000 degrees. It's gonna take a little bit of time. It's gonna kind of heat up, and that's gonna be based over a certain amount of time. And this will be our temperature. We'll just say Fahrenheit degrees there. Okay, that's our temperature. So we're going to have a certain amount of rise in temperature over our time. That's how long it takes to heat up. And it doesn't necessarily cool down as fast as it does heat up. So then our cool down time could be a lot different. Maybe it cools down a lot faster. So now it might cool down a lot faster. So now our time is from here to here is our cool down time. Okay? And it will learn that characteristics. Okay, not everything's linear, but like temperature and stuff like that, so it's almost pretty linear as that thing starts heating up. It's not quite linear, but and so that's why we simulate a lot of our signals using the triangle wave, because typically a lot of our other devices are very linear and stuff. So if I heat up the heating plate, it's going to heat up from 70 degrees up to 1000 degrees, and it's going to take a certain amount of time, and as that thing starts heating up, it's going to gradually increase. Then the cool down time, if I got a lot of massive steel on it and stuff like that, it could wick away that energy a lot faster and cool it down, and it might cool down a lot faster. So our PID controller will learn them characteristics. And it knows that then, if I want to go from 70 degrees to 90 degrees or something, it knows what that rise is, that rise over the slope. It knows what that is, and so it can become very predictive. It knows that if I keep it on a certain amount of time, if I shut it off at this point, then I know that it's going to that much more time. And that even gets to be even a little bit more on the complicated side. Because it can actually, how do I want to say that? Because it knows what that, once it learns this and this, it can kind of combine it. So then it knows what you know, if also I want it to be at 90 degrees, then it knows that it's going to heat up to a certain amount, but then it's going to take a little while for it to cool back down, so it's going to kind of get that it's going to become very predictive on how that heating characteristics of how fast that thing heats up and cools down. I'm trying to explain something that's a little bit more complicated than that, but I'll think I'll keep that back. I can't think of a good example how to explain that. But basically, it's just it knows what the rise of that temperature is over time. All right. So that's how we use op amps a lot. We're looking at signals and then we're using them as trigger points. Whether if it's a motor controller or a temperature controller or something like that, we're kind of using them as. And then we're kind of using the actual, you know, if it's a motor controller, again, you know, we might want to say that at 1,000 RPMs is equal to my 0 volts. So if I want to maintain something at 1,000 RPMs, I can set it up saying that my reference voltage is going to be 0 volts, and it's going to turn on and off that motor so it maintains 1,000 RPMs. And what we do is we use we call them tachometers. So if I have a motor, again, everything has some type of a feedback. That's what we call like a closed loop system. So here's my motor, and coming out of my motor is what we call our tach. And basically all that tach is just a generator. It's just a generator. And that's our feedback. So one end will go to our ground, and the other one comes back and comes into our VN. And we just say that we just want to maintain 1,000 RPMs. As this motor starts to spin, spins our tachometer, it starts producing a voltage. The faster we spin this tachometer, the higher our voltage goes. So our voltage on our output of our tach starts to rise up. So what we do then is that once we get to that certain voltage, once that tachometer, let's see, what would be, I don't know if this would be, should go back to, we should go use our threshold on this one. Because 0 volts isn't a good one for a tachometer. But anyways, the tachometer will send in a voltage on here, and then the op amp will compare it with our reference voltage, and it'll turn on and off our motor controller. And then output can go right into our motor controller, and that can turn on and off our motor. Okay? Again, a very basic concept of why we want to use a comparator. There's a lot more to it than just turning on and off a motor. We actually use what we call pulse width modulation and stuff like that. But for the basic part of it, you know, we're just turning on and off our motor. So let's come back to the motor one when we're looking at our second lecture, our threshold one. Because that one's a better one for the motor one. The temperature controller is a good one for this one, but it's not good for the motor controller. So let's take a look at our next one here. All right, any questions on that one then? All right, let's look at 19-3, the threshold one. All right, so here's the threshold one. All right, so just like any other circuit and stuff, we can start analyzing it. What is my voltage going to be right at this point here? How do I calculate it out?
R5 divided by R4 R4 plus R5 times VCC.
Yeah, so basically it's just a voltage divider. It's going off my plus 5 volts, or my plus, whatever my source is, and then it's just dividing up my voltage. And that's going to be our new threshold voltage. So basically it's just our voltage divider formula, so figure out what our VRN is equal to our, because it's going to be, again, it's everything is referenced to ground, so if I'm referencing it to ground, I got my black lead on the ground, I got my red lead on pin 2, or on this point right above R5, basically I'm measuring the voltage across R5. So whatever my voltage across R5 is what's going to be at my input pin 2. So VRN is equal to then R5 divided by R4 plus R5 times my voltage source. So on here, my voltage source is going to be my plus and minus 15 volts. So what is my voltage then going to be at test point A there? What is it?
6.07 volts.
0.07.
Yeah.
Okay. Now, does polarities matter?
Yes.
Yeah. The plus or minus, or is it plus or minus?
Plus.
Plus. Yeah. So because that does matter. We have to watch out for our polarities. Anytime we have a test point, we have to make sure we have our polarities. So my current path is negative positive. My current's flowing north there. My voltage drop across here is going to be 6.07. That's going to be my voltage. So that's going to be my, that's going to be what my new reference voltage is. So I can set up, my own reference voltage. So if I have, what's my V second equal to? So I have plus or minus 15 volts going into my op amp. What's my V second equal to?
13.5.
Yeah, so it's going to be going both positive and negative 13.5 volts. Okay. So if I put in, plus 2 volts into my VN, what's my VL going to be? So we got somebody that's at 13.5 volts. What else? Any other guesses?
So it'd be inverting negative 13.5.
Yeah, we got negative 13.5. All right, any other guesses? All right, how many say that it's going to be the positive 13.5 volts? How many are going to say that's the negative 13.5 volts? I mean, all you guys cowards and afraid to...
I'll hold up to it.
All right. Bob's got... Well, we know what Bob's got. Yeah, it's going to be our negative 13.5. Again, which one is going to be... Which one's more positive? My plus 2 volts or my positive 6.07 volts? Which one's more positive?
Positive 6.
Yeah, the positive 6.070. So that one's going to be more positive. And I look at what pin it's on the inverting pin. So this one's more positive. It's on the inverting pin, so it's going to go to a negative 13.5 volts. Just another open loop comparator. The only difference is that we're just, again, now we just have a threshold voltage of whatever we want that half to be at. We can set that for whatever we want. So if I'm at plus 7 volts, what's my output going to do? It's going to be positive because this time my positive 7 volts is more positive and it's on the non-inverting pin, and my output is going to go to more positive. So then again, here's my I'm at my 0 volts. What's it going to take? So right now it's unpredictable. We don't know what the output's going to do. But let's just say right now it's we'll just say that it's sitting at 0 volts right now. Or let's say that it's at our negative saturation. So we'll say that it's at negative 13.5 volts. What's it going to take before that thing gets to go? That's going to make that thing positive. What is it going to take to make that thing to go more positive again? And what voltage is it going to make it go positive?
Plus 6.072.
Yeah, so it's going to be, so we know that we have to have, here's our reference voltage, and to make it predictable, then we know that we have to add on another 2 millivolts on it difference to make sure that we know that it's going to go positive. So at this point here, it's going to be 6.072 volts. And then at that point, then that thing is going to toggle up. And it's going to stay high until it gets to what voltage?
Plus 6.068.
Yeah, then it's going to go to positive 6.068 volts. And then that thing's going to toggle low again. And it won't do anything all the way through this whole section here because this is always going to be more negative than our threshold voltage. And so it's going to stay low until it gets up to our next toggle point, which are these two right here. Then it's going to go up. So that's what our output signal would look like then, as we send in that triangle link. As long as it's greater than our 2 millivolts, greater than our threshold voltage, it's going to stay high. Once it goes 2 millivolts below our threshold voltage, then it's going to toggle low. So this one here is going to be our upper toggle point, and this one's going to be our lower toggle point. Where does it switch from a high to a low? Or where does it switch from a low to a high? So that's what our output waveform would look like on this one. And what we can see then is also that what we got then is what we have then is we end up is the frequency difference between this one and this one, is the frequency changed?
No.
Nope, it's the same. It's identical. Okay? So even if we look at our first toggle point here, if we go from here to here, because it's all, our one complete cycle is from one point to the other, and we're looking at it from here to here. So this is where this one here also duplicates itself. So here's the starting of our cycle, goes up, goes up, goes down, and then right at this time where it's going to start up again, that's the beginning of our next cycle. And that lines up with this one. So the frequency is the same. What has changed on this now is what we call our duty cycle. So this is our duty cycle. And we went over this in chapter 8 and stuff like that. But now we're kind of bringing it into something. So this duty cycle has changed. Now, depending on a 50% duty cycle would look something like this. Okay, it'd be on just as long as it is off. That's a 50% duty cycle. So here we have a smaller percentage of duty cycle. We're only on. We're not on as long as we are off. So our duty cycle has gone down. It's less than 50%, and that's our duty cycle. And also another name for this is, we can call this our pulse width modulation. The frequency never changes, but if I change my threshold voltage, if I made this into a potentiometer, and I change that, if I change that potentiometer, and I brought that potentiometer all the way down so it brings it down to 0, so now my new toggle points are always at 0. Now what I just created was a 50% duty cycle, because again, it's going to look like our 0 crossing reference one, and that's going to give me a 50% duty cycle. It's going to toggle every time it hits 0. If I start increasing my voltage, if I bring this wiper down here and I get my full voltage, then what happens is that my toggle points start to increase up more on the tips here. And then these things, where it's turned on then, is going to get narrow, and my duty cycle is going to decrease. So we can also use that for what we call our pulse width modulation. We can adjust our pulse width modulation going into our motors. So now we'll bring back into that motor controller. And again, this is a very basic one, but here's our motor. Here's our tach. And our motor is going to come out. This is going to come out of our output on here. Ground. So what's going to happen, and we could actually, if we always wanted this motor, we don't want this motor to go into reverse, so I'm just going to put in a diode. So it's only seeing the positive, so it's just putting in a positive, all it's seeing is just the positive output peaks. Because remember, this thing here was going to a negative 13.5 volts up to a positive 13.5 volts. So if it was a DC motor, if my output went to negative, the thing's going to want to try changing directions. So if I only want to look at my positive voltages, I can just go ahead and put in a diode in there, and it's only going to look at my positive voltages. It's only going to turn on when I got my positive 1 voltages. So what's going to happen is, and I'm going to turn on that, so I'm going to turn that on, and that, again, let's say that at positive 6.07 volts, we'll say is equal to 1,000 RPMs. So at 1,000 RPMs, I want to get this motor so it's running at 1,000 RPMs. So what happens is that this tach here is going to be outputting, let's just say that at this point in time, this tach is going to be outputting, let's see here, let's see how to make sure. I should probably change my diode, because that's going to go. I'm going to change my diode. I'm going to make this a negative going. Yeah, I'm going to make this one a negative going. So we'll just say that my tach is outputting 5 volts. Okay, my tach is outputting only 5 volts. So we know that we're not up to 1,000 RPMs yet, because we know that 1,000 RPMs is at a positive 6.07 volts. We know that this one is going to be more positive. My output is going to be inverted, so I know that my output is going to go to a negative 13.5 volts. And what that's going to do is that diode is only going to let the negative voltages go in, which is fine. We can have this tied to a positive ground. We can have that one tied to positive, doesn't matter, it's still my same ground. My diode is still going to drop its 0.7 volts. The remainder amount of voltage is going to go to that motor, and that motor is going to start to turn on, it's going to start to spin. as that motor starts to spin, then my tach, as that tach starts spinning faster, that voltage is going to start to increase coming out of my tachometer. And eventually it's going to get up to positive. We'll say now this time it's kept on spinning. We'll just say we overshot it. And it went up to a positive 7 volts. Okay, because well, here, let's do it this way. Let's say that we can see it. We'll just say it went up to a positive 6.07 volts. It's equal to our thing. What's going to happen then is that once it gets to that, and once that voltage there, now it's at a positive 6.07 volts, it's kind of going to be unpredictable at that point. So right now, it's just right on that toggle point. It's just ready to go. And then when I go to 2 more millivolts higher than this voltage, what's going to happen is that this one's going to become more positive, and my output is going to turn to a 13.5 volts. So then what happens is that my diode is going to stop any of my positive voltages, and it's going to shut that motor off. It's going to shut that motor off, and then the tach's going to start to slow down. And once that tach starts to slow down, it's going to drop below that threshold voltage. This is going to drop below there. It's going to start to slow down. Then this one becomes more positive, and it turns my motor back on. And it sits there, and it's going to turn that motor on and off. It's going to give me a duty cycle. It's going to just sit there, and it's going to just toggle that output on and off. And it's going to just sit there and toggle that. And it's going to sit there and make that motor run at 1,000 RPM. And it's going to kind of sit there. And it's going to have, because we don't have all total control, but that RPM, if I was to graph out the RPMs of it, it's probably just going to be kind of overshooting and undershooting and overshooting and stuff like that. But that RPMs is going to be like this. If I had a PID controller on it, then I could accurately calculate how long it takes to slow down that motor or how fast to speed up that motor, and that controller can control that. But in a very basic form, I could actually make my own very simple motor controller and turn on and off the motor running the tach. And that's my feedback. My tach is my feedback. It doesn't have to be a resistor. It can be any voltage. And that's my feedback. And that becomes a closed loop system now. Even though we don't have closed loop feedback, can be like an amplifier. Okay, we could have that feedback resistor in there, or we could have some other type of device, and that tachometer replaces that feedback resistor, and now the tach becomes my feedback device. And now it's very controllable. The gain on that is very controllable. It's going to maintain a certain voltage, or a certain, in this case, a certain speed of that motor. Just using that reference voltage as the indicator. And we could even actually, if you get time, we could actually, I can probably dig up a couple of DC motors, because a motor and a tach, basically they're both one and the same. I can take a motor, I can put 2 motors together. If I spin one DC motor, it becomes a generator. If I apply voltage to the motor, it spins. If I spin the motor mechanically, then it becomes a generator. And we could actually create ourselves a very basic motor controller using the op amp using this lab. If I want to change the speed on that, then all I have to do is I just have to take the 68 kilo ohm and put a potentiometer in there. As I change my potentiometer, so if I bring this up to 0 volts, that's my reference voltage, then my motor is going to actually stop. That motor isn't going to even want to hardly spin, because it's going to want to make sure that it maintains 0 volts on the output of the tach. The only way I can get 0 volts out of the tach would be not to spin the tach. So if I change this to a potentiometer, brought it up to so that it's 0 volts now on my inverting pin, that motor would basically just try and stay shut off. It's going to toggle back and forth. It's going to try running it, but every time it starts to run, it's going to shut itself off again. If I bring it all the way down and I increase my reference voltage up to 10 volts now, then that motor is going to try spinning that tach faster, so that tach produces a 10 volt signal. So now I just measure myself limit, and I can control my speed of my motor. up and down. So the op amp, the open loop comparator op amp, or the op amp itself, is very basic, but we can do a lot of things with it. It's just a matter of what do we hook up for devices up to it. If I'm just using voltages, it's pretty straightforward. And it's very straightforward. We just have to determine what's my reference voltage and what's my feedback voltage. And that's why I'm just comparing those two voltages at all the time. That's going to determine what my output's going to do. All right, any questions on that? All right, let's take a 10-minute break and then we'll beat you up with the window detector one. That's the big one. That's 19.4. Lecture 19.4.
For my dad?
Oh, yeah.
For my dad?
Never got text
Okay,
message.
5 minutes. I know. Still running?
What's his number?
Best part.
That's the
Oh no, I got a random phone call yesterday when I was at Easter. I didn't know who it was and I wasn't expecting one. But
Yeah.
no, I haven't heard from him. If he texts me, I'll have him call Scott. He's our sales or like the guy that like helps you figure out pricing and like what kind of door.
Yep.
Because if he wants
It
a
said something about a 5-fold.
where it folds up like
This one here,
twice, I don't know what that is.
Positive peak, right?
This way?
And this one here is going to be the negative peak. So every time this thing goes low, from here to here,
But either way.
from here to here, I want my output to go high. When this thing goes low, I want this to go high.
Oh.
Right? Because I'm detecting my negative peak this time.
Yeah.
Now, more people will struggle with that one.
Okay, you can't detect your negative peak when it's in the, like, the lower.
You could, but typically, what is the true? A high or a low? A high. So a high would be is what we want a true. So yeah. So on the negative peak detector, then, if I'm detecting, I want to detect